Well, we are going to continue on in Chapter 8 here with round things. Now, round things deserve a little bit of special consideration, special treatment, because like every object, they have a weight and some contact surfaces and contact forces. But with round things, the normal force goes through the center of gravity. So let's just go ahead and put the contact surface right there, contact force, and the line of action goes right through the CG. Same over here with A. So here we have a contact surface here, contact force, normal force, and it goes through the center of gravity. All right, as we pull up on this spool, it's going to tend to rotate a little bit, which means it's going to move. One thing that's kind of obvious perhaps is that there is no movement without slipping in this scenario. It can't move at all unless it slips. So as it slips, we see point B moving to the right, which means that the force of friction would oppose that and would go to the left. Because this is a slipping scenario, I know that that's going to be equal to mu B. At A, we also have a friction force, which is going to go up. And that will be mu times A. And let's not forget our gravity, this mg coming down. All right, there is no one right way to solve these problems, so just experience will help you determine a path or a process, but I'm going to sum the moments about O is equal to 0. O I'm calling the center there, the middle. So here I have P times 0.6. Let's just look at the lever arms. P coming up, it has this lever arm. It's trying to go in the counterclockwise, so that's positive direction. Then the rest of the forces, A goes through O and B goes through O. However, the forces of friction have these lever arms, which is 0.9 for both of those, and they're both trying to go in the negative direction, so I'll say minus mu A times 0.9 minus mu B times 0.9 equals 0. All right, I have three unknowns in that equation, so I can't really go very far. Let's do another force or another equation. Let's do some of the forces in the x is equal to 0. So here I A minus mu B is equal to 0. And again, that's can't solve for anything quite yet, so let's use our last equation. Sum of the forces in the y is equal to 0. So here I have plus P minus mg. What else do I have? I have plus mu A plus B equals 0. So I have a three equations, three unknowns scenario here. And there's multiple ways of solving this, but I'm going to say that A here is equal to 0.3B. I'm going to plug that into there, and out of there I'm going to find that B is equal to 1.709 P. And then I'm going to plug that into that equation, and then I'll need this in that equation as well. And I can do a little algebra, and you'll see that P is equal to 342.7 newtons. Okay, so that's the algebra way is can be a little bit tedious, but you guys are good at algebra, so I'm sure you'll do fine at that. Another way of doing this is with RREF. We do have three equations, three unknowns. So let's just look at the way to set this up with RREF, and let's see if you can relate to this. In this case, what I did was built my three unknowns and three equations into my matrix. So here are my three equations. Here are the three unknowns, P, A, B, and then of course they have to be equal to a K. So let's just follow the coefficients and make sure. Sum of the moments. So I have P has a coefficient of 0.6. A has a coefficient of 0.3 times 0.9, and that's negative. B has a coefficient of negative 0.3 times 0.9, and there is no constant there. Some of the forces in the x. I have A is a coefficient of 1, B is a coefficient of negative 0.3, and in the y, P is a coefficient of 1. Mg happens to be the constant, so if that goes over on the other side of the equation, that would be 100 times 9.81. A has coefficient of 0.3, B has coefficient of 1. Use your RREF function, and again, refer to the tools on Blackboard resources, and you'll be able to get there, and you should get these answers, A, B, and P. Okay. Actually, I didn't write down what A and B are, but RREF will give those to you, and I should have done that, but I didn't. All right, here's another spool problem. This one has tied to the wall here. And again, this is a no movement without slip scenario. And you can kind of see what would happen if there isn't enough friction. It would rotate and fall. It would rotate, fall, and then it would slip here at point A. So let's go ahead and draw the forces on our picture. And I'm going to say that there's going to be an mg. There's a normal force. There's a force of friction, has to go this way. And why is it going that way? It rotates this way as it falls, which means that the force of friction has to be pulling it up. There's also going to be a tangent or a tension in the rope that looks like that. The angles here are 60 degrees, which means that this is going to be 60 degrees. And we won't need it right off, but I'm going to put a T cos 60 and T sine 60 as part of my force breakdown. Okay, let's see what we can find. Let's sum the moments about the center again, and or sum the moments about the center and see what we can come up with. So sum the moments about O is equal to 0. And what we're looking for here, I guess we should talk about this, but determine the coefficient of friction, the minimum coefficient of static friction to keep it from falling in this scenario. So let's see, what have we got? Sum of the moments about O. Mg goes through O. A goes through O. Tension actually has this lever arm. It has the radius. So whenever you see a tension on a round thing, it is the moment caused by that is just the tension times the radius. Don't try to break it up into its XY components and then find individual lever arms. You'll get lost. So just tension times the radius. In this case, it is 0.3, and it's going in the negative direction. So I'll say that it is minus tension times 0.3. Then what else do I have? I have the force of friction, which would be positive mu A times the lever arm of 0.6 is equal to 0. So here I got mu A is equal to T times 0.5. All right, got two unknowns, three unknowns actually. I don't know mu or A or T. Let's see what else we can do. Let's sum the forces in the Y. Here I got minus mg, I do know that, is 50 kilograms, plus T cos 60, plus mu A is equal to 0. So I can fill in a little bit of the gaps here, 9.81, plus T cos 60, plus, and I know mu A is equal to T times 0.5. Wow, look at that, that's equal to 0, so I can solve for the tension here with that equation, 490.5 newtons. All right, that's still not getting my coefficient of friction, so let's sum the forces in the X is equal to 0. See what I can find. T sine 60 minus A is equal to 0. So here I've got a T of 490.5 sine of 60 minus A is equal to 0. So A here is equal to 424.78. And then going back up to here, I can plug both of these into there and find out what mu is. And so the mu here is equal to 490.5 times 0.5 over 424.8, and I get that is equal to 0.577. So again, that's the minimum mu required to prevent slip. If mu is greater than that, obviously it wouldn't slip any more than it's already slipping. If mu is greater than that, it wouldn't slip at all. If mu was less than that, it would slip. It would slip more easily, I suppose. So mu has to be at least 0.577 to keep it from slipping. All right, here's just a couple more round things to consider. I'm going to give these to you for homework, I hope. But in this case, there's, again, a spool on a consideration, no movement without slipping. So in this case, what direction is it slipping? It looks like it's going to slip in this direction. So it's going to slip like this. The normal force is going this way. So in this case, if it slips that way, this part here goes this way, which means that the force of friction is going down the hill. That will be whatever this surface is. We'll call that A. This will be mu A. Still has a mg sine theta, mg cosine theta, and it will still have a tension in here when you evaluate it. But the key thing is to try to figure out what the coefficient of friction is to keep it steady there, and making sure that you understand the direction of the force of friction as it moves. All right, the next one is this one with a little step. We did a little bit of this in chapter 5, I believe, and so let's just do this one more time. And here you have to determine whether it slips. In other words, it could slip here at A and B, or let me move this back over here, or it could stick and just roll over. So that's kind of the question is what happens here, and you have to determine a little bit of have to do a little bit of condition questioning. You have to assume one thing and see if it's true, and then assume one thing and see what the force might be required, and then assume another thing and see what the force might be, and then compare those two. But let's remember our trigonometry. That's kind of one of the key things. Again, A goes through the CG. In this case, if it slips, the force of friction will go this way, and then there's going to be a contact surface at B, which will also go through the center of gravity. And the force, if it slips, then the force of friction will also be opposing that slip. So this will be mu A, this will be mu B. Now remember what we did before in terms of the geometry. We said that there is a little triangle that's formed here with an angle theta. That's going to be the same angle as this theta. And this is a height h, which is given. We obviously have a radius, and so we're going to say that this distance here is r minus h. And I guess that's angle theta as well. And then this distance here is r sine theta. And this distance is equal to r cos theta. So using all those relationships, you should be able to sum the moments about some point. Don't forget the mg here, because that's what is required. So if you sum the moments about B, you should be able to get this times this lever arm, mg times this lever arm. You should be able to find out what you need. The slipping condition is a little more difficult than the non-slip situation.